algorithms. Today we'll be discussing the models of computation and increasing runtime efficiency. The basic guideline of this lecture will be, to quickly recap on last lecture, to make sure you're familiar with what was going on, just in case you're not watching this back to back. Discuss asymptotic analysis, which will probably delve deep into, big O notation if you're not familiar with that already. Discuss the model of computation and Karatsuba's multiplication algorithm, which is actually used in Python. So, let's recap on lecture 1. So, lecture 1, we discussed what an algorithm is. It's the sequence of instructions that the computer can carry out in order to intake inputs, whatever these inputs may be, and output the specified output, deterministically the output. It should be efficient in terms of runtime, which means, operating very quickly on large data sets, because that's what we look for as users. We want things to be fast and efficient. You wouldn't want to come to your web page and it take, probably over 2 seconds to load. In fact, it's probably only 1 second, because most users will want things to be within milliseconds of time. But to continue on, we also spoke about, finding peaks in 1D and 2D arrays. You can comment to ask for how to find them in 3D arrays if maybe you tried them yourself and weren't able to figure out how to do that. I can post a video on that if you all would like me to. So, asymptotic analysis. So, asymptotic analysis is what we will use in this series in order to quantitatively describe the efficiency of an algorithm, right? What does this mean? When you determine whether or not an algorithm is good, you really need to understand how it works on specific data sets, right? If you look at your algorithm as this black box, I have no idea what procedures are taken. I simply give it inputs and I expect a certain output. So the first step is to make sure that the outputs are correct, right? But now we need to dive deeper. We need to really distinguish good from mediocre from bad algorithms, right? So a good algorithm, right? To really understand what a good algorithm is, we need to take on this idea of prepare for the worst. That's how we should make our algorithms work. They should prepare for the worst, which is analogous to the worst case testing strategy. So as you can see, there's 3 different test cases. You have worst case, average case, and best case. All right, best case and average case can work sometimes if you don't need your algorithm to be very pinpoint, depending on what you're trying to do, what the algorithm is for. But in this lecture series, we'll be using worst case all the time, okay? And worst case is, maybe you're working with a sorting algorithm, right? To understand a worst case, depending on what that algorithm does, we'll see how it runs on a exactly reverse ordered an array, right? So say we wanted you to, take in a list of integers and produce them in incrementing order, right? Then maybe the worst case for that algorithm would be to give you a list of integers in decrementing order, and let's see how it operates on that. And so that's the main idea of this practice. Try and get the worst case inputs and see how your algorithm faces that. Because we really want to try and break these algorithms. That's how it tests well. You don't want to give it the best inputs, because then how do you know if it would ever break? But now let's discuss a bit about the different notations we'll use in this class. So big O. Many of you may already be familiar with this. It's just a quick recap on the very common big O notations. So you have constant, which is, as you can see, doesn't vary at all depending on the input size. It should always run in constant time. You have log n, operating on 10 things. You If we count like units of time, it'll be 3. Operating 100, it'll be 7, and so on and so forth. As you can see, the worse the runtime is, the more poorly it will operate on large data sets. You can come look back at this later on. Maybe pause it if you really want to look at the difference between the two. The different runtimes. And this is a nice graph. I think this is a bit more intuitive as to how they actually operate according to each other. So as you can see, constant is this blue line right here, straight across. And then you have log n, which is the next order, and then n log n squared. This orange line is 2 to the n, and then you have n factorial. I personally like to remember a graph like this because it really gives me an intuitive understanding of how it looks and how they match up with one another. And so yeah, maybe you could look back at this later on. So now to move forward into models of computation. And what is that? What is a model of computation? So there are two things we need to do in models of computation. Specifying what operations our algorithm can perform. Correct? So you don't want to. There's a specific set of operations that your algorithm can do. Some may take too much time; they're too costly. Maybe multiplication just isn't the same as addition, and you can't count those as the same, especially when dealing with large numbers. And we'll get into this later on when we explain Karatsuba's multiplication algorithm, because there are differences in runtime for each different operation. And you really need to take that into account when you're dealing with making efficient algorithms. Next, we need to understand, as I sort of already went into, how much time is spent for each operation. Very crucial, very crucial. Remember to think about how much time is used on different, object or structure operations. Operations on a list may be completely different from operations on a dictionary, and so on and so forth. And some, you have to really understand the trade-offs. Some are better than others. So the two models that we'll look at is, the earlier model, which is very simple. You can probably look this up. I can't quite remember the computer scientist who created this this model, but it didn't quite reflect, it wasn't very reflective. It wasn't a very good model. It really hid a lot of the internal times, you can say. And then the present model, which we'll use for this series. So the earlier model, they allowed every operation, addition, multiplication, subtraction, and division, to all be 1 unit of time. Why is that bad? Why not just model every single operation? It's a simple operation that we've been doing since 5 years old. Add, subtract, all these big, really simple operations, multiplication, division. Well, there's a mistake with that, right? So if you have very large numbers, and say you're doing, some really large prime number times another really large prime number, as we did in, I don't know, second, first grade or so, you multiply every digit in the second number to every other digit. You make sure you carry down the zeros and so on and so forth, right? That takes a lot of time. It's actually order n squared. And so you can't compare that to the amount of time it takes to simply add integer, because adding for a computer is very efficient. You can do binary addition in very micro scale of time. And so you can't do that. That's a very poor model. It was an early model, so it's fine. We grow, but it isn't. It won't work for this class. The present model is read access machine, RAM, for short, but it's not quite RAM like read access memory, which is a computer, but it's almost directly modeled as such. Why? Because we think that that's a good representation of how our algorithm should perform. So if we think of, this machine having a bunch of different slots, if you're ever taken, computation structures or a course of some sort that, really explain the hardware in computer science, then, you have these rows which can be filled with 64-bit words, and you can have different manipulations. The CPU can perform different operations, Boolean operations, addition, multiplication, subtraction. And so that's how we model uh, our computations for algorithms. This is a quick graph or view of how a quote unquote read access machine would look with all of these different rows, and you can have different numbers or your different words, what we call them, in each slot. And so as you can see, we can model up to 2 to the 64-bit size numbers, which is very large. Now for the fun stuff. Karatsuba's algorithm. And so as I was saying before, the standard multiplication algorithm runs in order n squared, right? You multiply every digit to its next digit. I wish I can show you here. I think I might show you in the next slide. But if you did 65 times 74, you do 4 times 5, then carry over the 2, 4 times 6, 24, add the 2, so on and so forth. But there has to be a better method, right? Of course. Very, very unique. So as we explained in the previous lecture, divide and conquer, which is a very key method that we'll probably use throughout this entire series. Karatsuba, was able to decrement the amount of operations per multiplication to 3 rather than 4, right? So first you have the binary number itself, right? You take off the digits, and you have this low, which would be like 32, and then the high, which is the other upper or the higher 32 bits or whatever it may be. And the same thing for y. And so now you can multiply distributive property, so on and so forth. You get the terms, x times y would be x low times y low plus 10 to the n x high y high plus 10 to the n over 2 x low y high plus x high y low. But when you simply do this, you still have 4 multiplications, as you can see. But how can we change that? How can we decrease that? Very clever trick. So when you evaluate x high, y high, and x low, y low, you can use these two answers to sort of conglomeratize one of the previous expressions that we had. So, for example, what if we did, as you can see, 10 to the n squared, x low plus y low, x low plus y high. So those two addition operations are simple addition. And then we multiply those sums together. And those sums give us this other long operation. But when we subtract the x high and y high and x low, y low that we found previously already from these two operations, by having this one and this guy, right? We can simply subtract it, and then we'll end up with just this right here, right? Cool. So that's a very clever trick. I think it really shows how you can be clever at divide and conquer algorithms, and how they can be very useful. And so instead of 4 operations, now we have 3. So now you have 3 times, half the time it would take to operate on the next half of the size integers, correct? Then you have 9, because now you're just going to completely, substitute this in here, continuously do that all the way until what? As we said before, log n. That's how much time it would take to continuously divide in order to get to 0, correct? That's how much time it is. So now we have 3 to the log base 2 of n. A quick mathematical manipulation, you have 2 to the log base 2 of 3 times log base 2 of n, which is also equal to n to the log base 2 of 3, which is a significant increase in the runtime of the standard multiplication algorithm, since log base 2 of 3 is equal to roughly 1.6, which is over much larger data sets or multiplication, is an increase, a significant increase in runtime efficiency. So I hope you enjoyed. If you have any questions or comments, please leave them below and subscribe to the channel. Thank you for your time.